Basics of AC, alternating current, detailed description. The image explains the basics of alternating current, AC, which is the type of electricity used in homes, offices, schools, factories, and most electrical power systems around the world. Unlike direct current, DC, where electricity flows in only one direction, alternating current, AC, continuously changes both its magnitude and direction over time. This change creates a smooth sine wave, which is the most common AC waveform. AC is generated by power stations using large electrical generators and is transmitted over long distances through high-voltage power lines before reaching homes and industries. One of the main advantages of AC is that its voltage can be easily increased or decreased using transformers, making it more efficient for long-distance power transmission with lower energy losses. The left side of the image shows the AC waveform, which is a sinusoidal wave plotted against time. The vertical axis represents voltage, V, while the horizontal axis represents time, T. The waveform rises smoothly from 0 to a maximum positive value called the peak voltage, Vp, then falls back to 0, continues to a maximum negative value, and finally returns to 0 again. This complete movement is called one cycle. The time required to complete one full cycle is known as the period, T, and the number of cycles completed every second is called the frequency, F, measured in Hz. In most countries, household electricity operates at 50 Hz, meaning the waveform completes 50 cycles every second, while in some countries, such as the United States, it operates at 60 Hz, completing 60 cycles every second. The waveform also shows the peak-to-peak voltage, VPT, which is the total voltage difference between the highest positive peak and the lowest negative peak. The image introduces several important formulas used in AC circuits. The instantaneous voltage at any moment is given by the equation V, T, is equal to Vp times sin, 2 pi ft plus phi, where Vp is the peak voltage, F is the frequency, T is time, and phi is the phase angle. This equation describes how the voltage changes continuously with time. The image also shows that the peak-to-peak voltage is calculated using Vp is equal to 2 times Vp, which means the total voltage swing is twice the peak voltage. Another important value is the root mean square, RMS, voltage, calculated as Vrms is equal to Vp2, or approximately 0.707 times Vp. RMS voltage is the effective value of AC voltage and represents the equivalent DC voltage that would produce the same amount of heat in a resistor. Finally, the image shows the relationship between frequency and time period using the formula F is equal to 1T, indicating that frequency and period are inversely proportional. The right side of the image explains how AC electricity is used in real life. Electricity is first generated as AC in a power station using a large generator. The voltage is then increased by a step-up transformer so that electrical power can be transmitted efficiently over long distances through high-voltage transmission lines. Near cities and homes, step-down transformers reduce the voltage to a safe level for consumers. The electricity then reaches household wall outlets, where it is supplied as 120 VAC at 60 Hz in some countries or 230 VAC at 50 Hz in many other countries. This alternating voltage powers common household appliances such as fans, lights, refrigerators, washing machines, televisions, air conditioners, and microwave ovens. Most modern electronic devices, such as mobile phone chargers, laptops, and televisions, first convert the AC supply into DC before powering their internal electronic circuits. The image also includes a practical example for calculating RMS voltage. If an AC waveform has a peak voltage, Vp, of 170 volts, the RMS voltage is calculated using the formula Vrms is equal to Vp2. Therefore, Vrms is equal to 170 divided by 120 volts. This explains why a household electrical outlet rated at 120 VAC actually has a peak voltage of about 170 volts. Similarly, a 230 VAC supply has a peak voltage of approximately 325 volts. Engineers and electricians use RMS voltage because it represents the effective voltage delivered to electrical equipment and simplifies power calculations. A simple real-life example is a ceiling fan connected to a household AC supply. When the fan is plugged into a 230 VAC, 50 Hz outlet, the alternating voltage changes direction 50 times every second. This changing current flows through the motor windings, creating a rotating magnetic field that causes the motor shaft and fan blades to rotate continuously. The fan converts electrical energy into mechanical energy, producing airflow that cools the room. Another common example is a room light connected to the same AC supply. The alternating current flows through the light bulb or LED driver, converting electrical energy into light. Although the current changes direction many times each second, the change happens so quickly that the light appears to glow continuously without noticeable flickering. A useful way to understand AC is by comparing it to ocean waves. Imagine water moving back and forth on the surface of the sea. The water does not travel in only one direction, instead, it rises and falls repeatedly. Similarly, in an AC circuit, electrons move back and forth rather than continuously flowing in one direction. The electrical energy is transferred through this alternating movement, allowing appliances to operate efficiently. This back and forth motion makes AC especially suitable for power generation and long-distance transmission. In summary, the image explains that alternating current, AC, is an electrical current that continuously changes its direction and magnitude, forming a sine wave. Important terms such as peak voltage, Vp, peak-to-peak voltage, VPP, RMS voltage, Vrms, period, T, frequency, F, and instantaneous voltage help describe the characteristics of AC signals. AC power is generated in power stations, transmitted efficiently through transformers and high-voltage transmission lines, and finally supplied to homes and industries. Understanding these basic AC concepts is essential for learning electrical engineering, electronics, power systems, motors, transformers, household wiring, and the operation of everyday electrical appliances.